Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is Digital 3, ET 123. Today we are going to finish our third and final act in the 3-act DSP play, namely DAC, Digital to Analog Conversion. So our basic block diagram, if we remember right, was ADC feeding DSP. Oops. Feeding our DAC. And if you remember right, here we're taking an analog signal, filtering it, sampling and holding it, and converting it to digital via quantization. Here we're compressing it, decompressing it, encoding, decoding it, amplifying it, attenuating it, doing some crazy math to it, whatever you want to for DSP, be it a radar application, a telephone application, whatever you want to do with that digital data. And now we're here at number 3, where digital data is being converted back to its analog form to be used. This could be someone talking to you via the cell phone network. It's all zeros and ones on this side, but you want a voice and analog signal to come out. That's what a DAC is, digital to analog conversion, taking digital data, putting it back into analog. Okay, so there's 2 basic methods of doing this. One of them is the binary weighted input method. Second one is a resistive ladder. And both of these methods use an op-amp to make it happen. Okay, so let's review our op-amps. This is, again, very basic description with a lot of mumbo-jumbo, magic tricks, and hand-waving intended for an audience with the basics of electronics, and not necessarily the whole truth, quote unquote, that you learn in ET 221 and 222. There's some cross-pollination between these courses, but I'm just trying to keep it to the big picture stuff without bogging us down in unnecessary details. So, if we remember right, an op-amp. Op-amp is a magic device with 2 magic properties. And it looks like our little triangle here. We've got an inverting input, the negative, non-inverting input, our positive, and our output right here. Okay, the first of our magic properties is an op-amp tries to hold the potential of the inverting input at the same potential as the non-inverting input. So if we ground our non-inverting input, what we get is a virtual ground at our inverting input. Okay? So now, here's an input resistor, and we apply a certain V into it. It stands to conjecture, because this is a virtual ground, current would start flowing in this manner. What is the magnitude of that current? I Vn divided by Ri. Okay, via Ohm's law. No stretch right there. But now that brings us to our second magic property, namely that no current flows into the op-amp. So we have this thing called an RF, a feedback resistor. So therefore, via KCL, Kirchhoff's current law, the current through Ri has to go somewhere. Because of the second property of op-amps, no current can go into them. It's got to go somewhere. The only option it's got is that current has to go through RF. Okay? So therefore, if there's current through RF, via Ohm's law, it stands to conjecture that there should be a voltage drop across RF. Okay? Equal to V out, I, which we just determined over here, times RF. But because it's flowing from our virtual ground, because they're trying to keep it at the same potential, we've got to accommodate for this direction of conventional current by adding a negative sign right here. Okay? So let's just do a quick example. I'm just going to do some random values here. There's a 10 ohm resistor. Here's a 20 ohm resistor. And let's say we happen to put plus 5 volts right there. So current's going to start flowing in through here. And again, this node here is held at virtual ground because the first magical property of operational amplifiers. And what is the current through there? Well, I is equal to 5 volts divided by 10 ohms. That should be 0.5 amps. Therefore, because of the second property of op amps, no current flows into it, so it's got to go somewhere. So 0.5 amps is being forced through our 20 ohm resistor. So 0.5 amps times 20 ohms. What is that going to be? It's going to be 10 volts. But because it's flowing from ground to here, this means that has a lower potential. It's flowing to something lower potential. We have to accommodate for that by putting a negative sign here. So negative 10 volts. And what we've created here is an inverting amplifier. Notice the fact that we had a plus 5 and now we have a negative here. So plus to negative, inverting. And then amplifier, we've gone from 5 volts to 10 volts. We've doubled that. Okay? And it's dependent upon this ratio, V out, V in is equal to negative RF, RI. And basically what we've got here is that's our inversion because it's negative 10 volts. We have 20 over 10. It's basically making something negative and 2 times as big. We put in 5 volts, got out 10 volts. Okay, and understand there are limits to this thing here. It's, you know, what's not shown is that there's typically a negative 15 and a plus 15 power supplies, and it could be different values too. There are limits. You're not just going to put in like a 6 million ohm resistor here and expect it to be 6 million times. Yeah, there's limits, as you probably have discovered in 221 and 222. But I digress. We're talking about digital to analog conversion. So how do we use our op amps to perform digital to analog conversion? Well, our first method here is our binary weighted input DAC. This is method 1. And basically, this is where you put a number of resistors of very specific magnitudes, and they're connected to the input of the op amp, and are in turn supplied with voltage values representative of the binary code you're trying to convert back to analog. Okay, that's a mouthful right here, but basically let's go ahead and just, here is our little op amp. And that's no stretch right there. That's what you got to do. This is our output here. But where I say a number of resistors of very specific magnitudes are connected to the input and are in turn supplied with voltage values representative of the binary code you are trying to convert back to analog. Okay, so the binary code, let's use a 2-bit example. We've got 0, 0, 0, 1, 1, 0, 1, 1. That represents the total range of values. So it stands to conjecture 2-bit code would require 2 resistors, where this is the input Q0, and that's the input Q1. And let me erase these guys since we all know that, where this is the LSB, and that is the MSB. And we all know that a 2-bit binary code, the lower order bit represents 2 to the 0. The higher order bit represents 2 to the 1. And if we had 3-bit, it would be 2 to the 2, 2 to 3, etc., etc. But now what we do is arrange our resistors of very specific magnitudes inversely. Okay? So that gets R, whatever it may be, 10, 20, whatever. This one gets 2 times R. So if this was 10, then that would be 20. Okay? And you'll see how this works. Okay, so this here could be any value, 30, whatever. And we'll just see how this works now. And let's just go ahead and stick with these examples right here. So 10 ohms, 20 ohms. Okay, and we want to provide a 2-bit binary code input. And we want analog out right here. So digital in, analog out. So obviously when you provide 0, 0, and I should actually write it MSB to LSB, even though they're the same. So when I say 0, 0, you would expect 0 volts out. And that's not very hard to do, because if there's 0 volts, I'm going to get rid of some of this stuff right here. 0 volts, 0 volts. There's 0 right there because it's being held at virtual ground. There's no potential difference, and there's no current here, no current there, meaning there's no current there, and you get our expected value of 0 volts. Okay? But now we want to go ahead and step up. So we went from 0, 0, now we want to go to 0, 1. So MSB 0, LSB 1. So that's now 5 volts. Okay, so 5 volts, because this is being held at virtual ground, across a 20 ohm resistor. 0.25 amps. It's got to go somewhere. It goes through here. So 0.25 amps times 30 ohms, negative 7.5 volts. So 0, 0 gave us 0 volts. 0, 1 gave us negative 7.5 volts. Now, let's go to the next one. 1, 0. MSB 1, LSB 0. So now we've got 5 volts across 10 ohm resistor, 0.5 amps. Oops. 0.5 amps. 1, 0 gives us a value of negative 15 volts. So we've gone a step, negative 7.5, negative 7.5. How much are you going to bet 1, 1 gives us a step of negative 7.5, an equal step? Let's see if that happens. Now, 1, 1, 5 volts, 0.25 amps, 0.25 coming in here, 0.5 coming in here. What's going through here via KCL? 0.75 amps. 0.75 times 30, negative 22.5 volts. A step of negative 7.5 volts. So what we have here, 0 volts. That's our representation of 0, 0. Now Along comes the 0, 1. We get negatives. I've inverted it here. I should actually be going down, but you guys get the picture. Negative 7.5, negative 15, negative 22 volts. Basically, 1 step, 2 step, 3 steps within our digital to analog conversion. I know it's super blocky right now. You know, I know there's only 3 steps there, but you can get super fancy with this, as you'll see. You know, our resolution, which is probably a good time to talk about this, is pretty limited. We can go from 0 to negative 22.5 volts in 3 steps. And noticeably, it's pretty blocky, not a smooth transition as we're used to in analog. So using 2 bits, there's only 3 possible levels there, so obviously it's not the best representation of it. You know, resolution is the number of steps. In the above example, we've had 3 steps above 0, and for some reason it's expressed as a percentage. In this case, it's 3 divisions, so we've got 1 in 3 or times 100%, so 33% resolution. Or the method I actually like better is you refer to your resolution in number of bits. You know, everyone knows, or will know at least by the next example, that 3-bit resolution is far smoother than 2-bit resolution, and 16-bit resolution is substantially more, more smooth than a 3-bit resolution. Okay, so let's try that. So let's do a 3-bit. Binary weighted input digital to analog converter. Okay, so we want to do 3 bits LSB to MSB. Let's call that Q0, Q1, Q2. And again, we've got to do our resistor magnitudes, very important, inversely. Okay, so the bigger the MSB, even though it's weighted at, in this particular case here is 2 to the 0, that's 1. 2 to the 1, that's 2. 2 to the 2, that's 4. Even though it's got the bigger magnitude, it gets the smallest resistor, R. This guy gets the larger resistor, double that, 2R. And this guy, the LSB, gets the double of that, so 4R. And you can come up with a pattern for this here. Let's just say R was 10. Oops. 10, 20, 40. Okay, and let's just use our 30 before here. So again, the pattern is basically LSB to MSB. MSB gets the smallest resistor and goes back. So if we did a 4-bit example here, Q3, that's 2 to the 3, which is 8. We would have to set it up as R, 2R, 4R, 8R. Okay, but I don't want to do that because that's going to take up too much of my time. Let's go back to our 3-bit example, R, 2R, and by extension your time because you're watching this. It's easy to get this concept. Okay, so here we go. We got, let's go back to our 10, 20, 40. Okay, 000. That's easy. No current anywhere. No current here, 0 volts. Okay, and let's do this in a particular manner. So we already did 0, 0, 000. Now let's do 0, 0, 1. Okay, so 1 is actually 5 volts, so 5 volts across to 40. 0.12, oops, 0.125 amps. 0.125 amps through a 30 ohm resistor, negative 3.75 volts. And now I know I could go, or actually, yeah, we're going to do that one. Let's do 0, 1, 0. So Q1 is now receiving 5 volts. So 5 volts across a 20 ohm resistor. What's the current that flows through there? Well, it's 0.25 amps. That means 0.25 amps through here. That means you're getting out negative 7.5 volts. Okay, now let's go to 100. Now you've got 5 volts across a 10 ohm resistor. So that's 0.5 amps. 0.5 amps through a 30 ohm resistor. What's that going to be? Well, it's negative 15 volts. Okay, so now let's just take, I know I skipped something from here to there, and the reason why I skipped that is because what's happening now, let's say, for example, we do 0, 1, 1. It's basically the summation of these two. Let's just draw that. So 0, 1, 1. We've still got 0.125 amps going there. We've still got, what is it, 0.25 amps going that way. So that means there's you're basically summing up the effects there. So you're getting negative 7.5 plus 3.75. What you get, negative 11.25 volts is at our output. What you've just got there, previously we were limited to, in our 2-bit example, 0, 7.5, 15, 22.5. And that was 0, 0, 0, 1, 1, 0, on 1. But now with our 3-bit example, we have gotten intermediate values in between this. 1, 2 steps, 3 steps, 4 steps, 5, 6, and I need to draw another one, 7 steps because we're using 3-bit there. So we're getting steps of negative 3.75 volts instead of giant leaps of negative 7.5 volts. And that represents, what was it? That was 0, 1, 1, and so on and so forth. Basically, you're getting these intermediate, i.e. smoother values. And now if we did, here, let's move this over. And actually just redo the whole thing here. You know, this whole comparison of this blockiness of the 2-bit. Notice how our 7 steps from, well, technically 8, well, it's from 0 because I don't really consider that a step, so it's 7 steps up. Our 3-bit it's still doing that same, you know, it's the same range of values from 0 to whatever the high could be. And by the way, you can change that high by the by changing this feedback resistor here, as have probably already seen in 221 and 222. And there's, like I said before, there's limits to it. You're not going to put a 6 million ohm resistor there and expect a 6 million volt gain or 6 million gain, So there's limits to it. So now notice here the resolution of a 4-bit. It's got twice the steps. Basically it's half of 3.75 steps. This was a 7.5 volt step here. Now we're jumping up 3.75, and now we're jumping up half of that. And how deep you want to go, 5-bit, 6-bit, 7-bit. You can go, the whole Pac-Man example. This is the old machines, and super high-tech, high resolution. You could go right down to the hair on Pac-Man's nose, just make it look that much sharper. Obviously it's going to take a lot more computing and processing power to do that, though. Okay, disadvantage of the binary weighted input digital to analog conversion method. It's not easy to mass produce these guys because the resistances, as we discussed earlier, it's this way and whoops, actually that way. They have to be pretty precisely matched in the inverse ratio to the MSB and LSB. It's R, 2R, 4R, 8R, 16R. So not so easy to mass produce these ones. So that disadvantage is countered in the second method. Basically, the resistive ladder method. Method 2, resistive ladder, digital to analog conversion. It gets around this by only requiring 2 different resistor values, namely R and 2R. Whatever the R value is, you need something twice as big as that. So 10 and a 20, regardless of what it is. You don't need R's, 2R's, 4R's, 8R's, 16R's, 32R's, or anything like that. Just 2 different types of R's. And how it does this, the resistive ladder digital to analog conversion method. Yes, it's using a op-amp to do this, but basically it's the special arrangement of the R and 2R resistors that makes this happen here. Namely, we're using Thevenin's theorem. And I know some of you guys are like, oh no, I forgot Thevenin's theorem. I'm going to refer you back to EET 111. And I know there's a video of mine on YouTube somewhere, so go check it out. Basically, it's making use of Thevenin's theorem and the proximity or distance of the input supply within the network to determine its effect on the output. And here's a picture that I'm going to borrow from your book. Okay, so this is the basic backbone of our resistive ladder network. And again, it's hooked up to our operational amplifier with a non-inverting input grounded. We've got our feedback resistor. And like I said, it uses a value of R and 2R. So our inputs are these guys right here. Now my LSB is the furthest away, and my MSB is the closest. I'm going to say Q0, Q1, Q2, Q3. In this case, it's a 4-bit. While I'm thinking of it, like I said earlier, that was the resolution there, 33% resolution. What is the resolution? Sorry for this digression. I was just thinking about that. I should probably mention that. This would be like, I think it was like 14.3% resolution. So it's one of 7 steps. Now this guy was one of 15 steps. So it's 6.67% resolution for a 4-bit, and on and on and on. But we're back at this. So LSB, most distant. MSB, closest. So what are these guys hooked up to? They're all hooked up to 2 R's. And it just so happens that the feedback resistor is also 2R. There's another 2R at this end, but in between is just R, okay? So that's what I'm saying is you just need two different resistor values. You don't need to have these 16 times and 32 times, okay? So now, what would happen if we were given an input? And let's start at an MSB, where just the MSB is high, okay? So you need to do some redrawing here. And what happens is, well, let's just draw with a digital input of, we want to say 1000, 1000, MSB 1000. We need to redraw this using Thevenin's theorem. Okay, since these zeros are all equivalent to a ground, we could flip these down here. And because they're equivalent to ground, we could just go click, 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 connect everybody together. And now, this is still 5 volts there. We still got to keep that up there because it's 1000. So now we got to figure out what is this mess equivalent to. 2R in parallel with 2R is an R. Let's do a simplified version. These two R's are in series, which makes it a 2R. In parallel with 2R is an R. R and R in series, 2R. 2R and 2R in parallel is an R. And I forgot this guy right there. R and R, 2R. Now we got to add these guys there. 5 volts, 2R. Since that one's grounded. What is the current? 5 volts. This one's ground right here, and the virtual ground right here. So there's no current, no potential difference between here. All the current flows that way. What is the current? Well, it's 5 volts divided by 2R. Since our feedback resistor also happens to be 2R, the current flowing through it is I equals 5 volts divided by 2R. And according to Ohm's law, the voltage would be equal to 5 volts divided by 2R times 2R, our V out. Well, I'm going to account for the fact that the current's flowing the other way here. Our V out is negative 5 volts. So through the magic of Thevenin's theorem, what we've created here is basically where the most significant bit produces a V out of negative 5. And if you do this analysis for something like 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, you would find, so that one's 5 volts, 2.5 volts, 1.25 volts, 0.75 volts as you go through. Ultimately, each lower order weighted input produces an output voltage that is successively halved, making the output voltage proportional to the binary weight of the input. Pretty cool, huh? So basically, if I did, let's see, I don't know, 1001, it would be 5.75 negative coming out because it's that guy and that guy. And I'll spare you the unnecessary details of going through summating those things. But basically, all it is the proximity or distance of that input through Thevenin's theorem produces an output voltage that is successively halved for each lower order weighted input. This kind of completes the resistive ladder digital to analog conversion method. And again, its advantage only requires two different types of resistors, R and 2R, something twice its value. So we've already discussed the term resolution, 4-bit, 15 steps, consider a 64-bit system. That's 9.2 times 10 to the 18th steps. Talk about the hair on Pac-Man's nose. That's right down to the DNA in the hair follicle on the mite on Pac-Man's nose hair. That's a lot of stuff. But let's talk about, let's see, what are the four terms that they want? Oh, it's accuracy, linearity, monotonicity, and settling time. Settling time, that's the easiest one. Basically, how long does it take? Because some of these things are real-time applications, just like a cell phone. You don't want to delay anytime someone's talking to you. How long does it take for it to produce its value? Someone talks, it's digital, and it takes 2 minutes convert from digital back to analog. That's not going to be a good conversation. Linearity. Let's use this example right here. Let's say this is what we expect. Here, okay, that's what we expect given. I think that was a 4-bit example. Quadruple 0 to quadruple 1. We expect something like that. And let's say we get something very similar. But notice how it's this guy's slope is here. It's slightly less, or for another example, it could be like that. Is it a linear? Is there an offset error? So that can have effects. Ideally, you want a linear, one-to-one correspondence between what you put in and what you put out. Each step is equal. Okay. Accuracy. Let's say you got 1100 and you expect 12 volts. One system gives you 12.5 volts. Another system gives you 14 volts. Which is more accurate? Obviously that guy. Okay, so just some basics. Resolution, number of steps within it, accuracy, how close you are to your expected value, linearity, as you step it linearly from quadruple 0 to quadruple 1, you would expect a one-to-one correspondence with equal steps in between. Settling time, how long it takes, and monotonicity, that is something you would not expect it to go from, let's say this value, you're stepping from here to there, to there, to there, to there. You wouldn't expect it to go back, to some value. Something that's non-monotonic. You would expect it to increase, It's not going to suddenly go down like that and then go up like that. That's non-monotonic. That's an error state. That should not be happening. Does not take reverse steps. Ideally, you want linear, monotonic, digital to analog conversion. Okay, so this is a end of DSP. We've discussed the general topics of DSP, including Nyquist sampling theorem, sample and hold, filtering, and then we've discussed ADC and DAC. This concludes DSP.